Hello and welcome to Diplomatic Derivatives. In today's video, we're going to talk about the Cayley table. This concept in group theory is important as it simplifies multiple other concepts of group theory. So let's dive right into it. What is a Cayley table? A Cayley table is like a multiplication table, but for a group or any set with the binary operation. Simply, it is a table which allows us to understand how group acts under the operation and whether it's closed or not, whether certain other properties of group is true or not on that particular group. So how are we able to make this table? First, it shows how the operation combines every pair of elements. For example, we take two elements 1 and 1, so it's a pair, and under the operation of addition, since in this example the operation is addition, how it combines. So 1 plus 1 gives us 2, and then you fill it up in the corresponding box. For example, the pair is 2 and 1, so 2 plus 1 gives us 3. You write it in the corresponding box, and in a similar manner you fill the rest of the boxes. Okay, then you fill in the table for each row and column. You write the result of the operation between those two elements. Now the main point is why is it so important? The row for the identity E and the column for E will just repeat the elements because E acts like do nothing. In the very first video of group theory lecture series, we saw that the identity E acts as a do nothing move, right? So what do we mean by doing nothing? The identity for addition is 0. Right, so the row for 0 and the column for 0 is just going to repeat the elements. Okay, so in the identity row and identity column, you will see a pattern, that is, it's just repeating the group elements. Okay, in a group, every element must appear exactly once in each row and column. So by looking at Cayley's table, what we will be able to understand is that once we see a particular row or a particular column, right, there is no repetition. So each element appears exactly once. If there is a repetition, it means that the given set is not a group. There has to be no repetition for it to be a group in any particular row or any particular column. If the group is abelian, the table will be symmetric, mirror across the diagonal. So the diagonal will have all similar elements, right? So if all the elements in the diagonal are same, it means the table is symmetric. And if the table is symmetric, it is an abelian group. Okay, so we don't have to perform the group axioms one by one to prove if it's a group or not. Just look at any row and column and you'll understand that if there is no repetition, it's a group. Again, you don't have to perform commutativity process again and again. Just look at the Cayley's table, and by understanding that the diagonal has all similar elements and symmetric, therefore it's an abelian group. So in this manner, Cayley tables allow us to simplify multiple other things in group theory. We'll take a look at one of the examples. It's a very simple example, modulo group Z2 0 1. So Z2 means number of elements is 2. Since this integer starts with 0 and 1, that is integers modulo 2, and the operation is addition. Now this is the Cayley's table for it. First we take the elements 0 1 in the first row, 0 1 in the first column. Right, now we've performed the operation. So 0 0 we have to add. 0 plus 0 is 0, 0 plus 1 is 1. So you see that the identity 0 is repeating the elements itself, right? Even in the column, 1 plus 0 is 1. So in the 0 column, the elements of the group are just repeating. 1 plus 1 is 2. And since it's a modulo group, 2 is represented by 0. So you get 0 here. Now you see no column or row has a repetition. So it's a group. And the table is symmetric because 1 and 1 is in the diagonal. There is no repetition. There is no different element in the diagonal, so it's an abelian group. Okay, that's what's written over here. Then we have example 2, which is Cayley table for Z3 with addition. Now Z3 means starting with 0 1 and 2, so 3 elements. Operation is addition. Again, very simple. 0 plus 0 0, 1 2, so identity will repeat the elements. Again, in the column it's repeating the elements. 1 plus 1 is 2. We write 2 because 2 is part of the group of the set, right? But when it's more than 2, so for example it's 2 plus 1 gives 3. 3 is represented by 0. Okay, and then 2 plus 2 is 4, and 4 is represented by 1. So 1 comes here. Now again, you see there is no repetition in any row or column, so it's a group. Also, the table is symmetric, so diagonal has a single element. Therefore, it's an abelian group. Now we look at another example, which is the same set under multiplication. So here is a difference. We see in the Cayley's table here, now since it's multiplication, the identity element is 1. So the row and column for 1 will repeat itself, right? Not for 0. For 1, the row and column, so if we look at the row for 1, it's 0, 1, 2, and column for 1, 0, 1, 2. Okay, so the identity is 1, so row and column for 1 will repeat itself. Also, we have to see that whether it's a group or not. So do we see it's a group or not? It is not a group. Why? Because 0, 0, 0, and here we have 0, 0, 0. There is a row and there is a column where elements are repeated, and for it to be a group, elements must not repeat themselves. Okay, so it's not a group, so obviously it's also not going to be abelian. So since it's not a group, we don't have to look for abelian itself, but just for the sake of an example, we see the diagonal is not same. There is 0, 1, and 0 in the diagonal. There is no similarity. Therefore, it's not symmetric and not an abelian group. Now, the problem with this Cayley table comes from the fact that there is a presence of 0. Now 0 is problematic. What it does is it kills everything. Multiplying by 0 always gives 0. So 0 is killing 1, it kills 2, you get 0 only. Therefore, it does not allow us to get this thing as a group. It's not a group. Now, we explain this concept in the next slide as well. Not every non-zero element has an inverse if you include 0. Now, this idea that 0 does not have an inverse, we have also already done this in one of the videos before, where we said that Z3 under multiplication, Z plus under multiplication is not a group. Right? You can refer to one of the previous videos where we tackled it in detail, but here we just talk about it in terms of the Cayley's table. So, what we're going to see is the fourth group axiom was proven that an inverse must exist, right? So for any element A, its inverse A inverse will give us the identity element. Okay, now here we have two tables for reference. We have the table for under multiplication and table for addition, right, for the same Z3. Now what happens is, for example, from the multiplication table we take 2. 2 multiplied by 2 will give us 4. 4 mod 3, since the mod 3 group will give us 1, right? So we get the identity element for multiplication 1 by what? By multiplying 2 with 2. So what, according to this equation, element with its inverse gives us the identity. Therefore 2 is self-inverse, right? So inverse exists for 2, right? If we take a look at 0, 0 multiplied with 0 will give us 0. 0 multiplied with 1 will give us 0. 0 multiplied with 2 will give us 0. In no way is it giving us 1, because we need one the identity element for proving that 0 has the inverse, right? 0 does not pair with anything else to give us 1. Therefore, 0's inverse does not exist. Okay, this table is a proof for that. Also, we see for this Cayley table for addition, 2 plus 2 gives us 4 mod 3 is 1. 2 plus 1 gives us 3 mod 3, which is 0, right? So this proves that with 2 and 1 we get 0. So 2 and 1 are the pairs. 2 is the inverse of 1 and 1 is the inverse of 2, right? Therefore, the inverse for 2 exists. By looking at the Cayley table itself, we can prove that by seeing wherever the identity appears. So for example, the identity appears here in this table. This shows us that the inverse of 1 is 2 and the inverse of 2 is 1. Identity appears here again, inverse of 1 is 2 and inverse of 2 is 1. So wherever the identity appears, those numbers are the inverses of each other. By looking here, we see identity for multiplication is 1. The inverse of 2, because 1 appears here, the inverse of 2 is 2. Again, identity appears here. The inverse of 1 is 1. Nowhere else does identity appears, right? Therefore, 0 does not have an inverse. That's a simple way to check, okay? So that's what's written here as well. So therefore, through this video, we are basically able to understand that in what all ways the Cayley tables helps us, right? First of all, the row and column for identity are going to be same. So in case of 1, this is the row and column for identity. In case of 0, this is the row and column for identity. They are same. To see if it's a group or not, we see that there is no repetition in any of the rows or columns. So there is no repetition over here, so it's a group. Also, to check the inverse, we see wherever the identity appears. So identity appears here, therefore the inverse of 2 is 1 and the inverse of 1 is 2. Again, here inverse of 1 is 2, 2 for 1. Okay. Also, to see if it's abelian or not, you see the diagonal, and if by looking at the diagonal we see if it's symmetric, therefore the set is abelian as well. So this is the importance of Cayley's table. Okay. Therefore, that's all for today. Thank you very much for this opportunity for me to be able to present to you the importance and relevance of Cayley's table. If you have any queries, you can write it in the comment box below. Make sure you like, share, and subscribe to the video in order for me to understand that you need more content that is going to make your life simpler. Next up, we're going to talk about the cyclic group and the theorems related to cyclic group. So this is a very important concept, and the theorems are very important in terms of examinations. So make sure you follow for more videos. And that's all for today. I'll see you in the next one. Thank you. Bye-bye.